So my name is Ken Ling, and I'm from UC San Diego. And today I'm here to share with you my research, MultiRepast4py, multi-layer agent-based simulation framework. So some motivations first. Before we begin on how we implement this multi-layer simulation framework, here are some motivations on why we need multi-layer and what a multi-layer network is at all. So the reason is humans are complicated. Ever since we were a child, we've been part of various networks, including family networks, school networks, and a lot more. Even the very conference that we're attending today can be seen as a kind of social network. And each of us carries a unique blend of social identities that shape who we are. We can also be seen as a bridge between networks, enabling the flow of ideas and information. And this conference is a perfect example of that. We bring research developed within our academic group and share it at this conference, with the agent or me itself as a bridge to share this information across different networks. So just like the graph shown over here, these three red nodes could represent one individual that coexist in three networks. And based on different contexts, we could simulate different things. Disease-like information also spread across networks. During the pandemic, the quarantine system showed us the importance of differentiating social networks. We're told to stay at home as it usually has a smaller size, and staying home avoid us from bringing viruses across networks, which could cause a wider spread if we're at school or a gathering like this. And this insight can only be reached when we view in a multi-layer network perspective and recognize the differences between the social networks. So let's take a closer look at the differences between networks. We mentioned size earlier, but there's a lot more to that. Networks also have different nature of interaction and frequencies. Hopefully we talk to our family a lot more often than the annual conference. And also the network structure could vary as well. On the left, the family network is smaller and it's more interconnected because everyone knows each other inside a family. So whereas school and conferences, we see this cluster-like structure, which could be different friend group, labs, or concurrent workshops going on. And in order to capture these differences between the networks, we need to use a multi-layer network, where each layer represents a distinct network structure and allow us to assign different frequencies and update rules. For example, if we want to simulate how conferences help facilitate information across schools, or how frequent we should host a conference to maximize the spread, we can create a multi-layer network with the two networks and then run simulations to analyze the information dynamics. So let's do a little recap. So far, we've seen that humans are complicated and their interactions span multiple distinct social networks, which is best represented by the multi-layer networks. But what's the gap? Like, what problem are we trying to solve here? So agent-based simulations has been around for quite a while, a little more than 50 years. However, it is predominantly single-layer models. For this reason, the pipeline is much more mature, having many platforms that's dedicated to single-layer simulations, including NetLogo, Mason, and a lot more. On the other hand, multi-layer simulations have gained popularity over the years as they more accurately reflect the complexity of human interactions. However, a gap remains in accessibility. Most existing simulations are highly customized for specific research projects and conducted by groups with stronger technical capabilities. As a result, the field is often gated by high technological barrier. In many cases, the technical setup is not the main focus of the paper, and when the code is not provided, reproducing the results can become a significant challenge. And here are some papers where researchers built their own multi-layer logic or even entire simulation environments from scratch. And there's a lot more that are not shown here. Much of this effort could have been avoided with the availability of a general-purpose, open-source multi-layer framework that lowered the entry barrier and enhanced reproducibility. So that's the goal of our project, to enable multi-layer simulations on top of existing platform to create a reusable, generalizable, and customizable framework that can be easily adopted in future research without needing to rely on the underlying logic. And after surveying a few platforms, existing platforms, we decided to go with Repast4py, an open source agent-based simulation software for the following reasons. As the name suggests, it's a Python-based, and with the various packages that comes with Python, users are able to make their model data-driven easily. More importantly, Repast4py offers high-performance computing that runs on multiple cores. This helps capture the scale and relevance details of many problems of societal importance. Last but not least, we share the same vision of providing an easier on-ramp for researchers from diverse scientific communities. And also, with Repast4py being Python-based, you can also make the agent a lot more complex. For example, like machine learning models, you can implement them on agents and provide a structured output. So how does Repast4py work? Repast4py reads the network file and creates agents accordingly. They also allow users to define events and frequencies at specific ticks of the simulation process. So what happens if we just feed the network we created into the model? What is missing? Why do we need this extra framework? So let's try doing that. Here we have a simplified conference and school network, which is stacked. Again, the nodes on the same vertical represent the same person. And once we feed it into the model, this is what it looks like. We lost information, and this is called flattening the network. Now, when given a node, we are not able to tell which layer it belongs to. And in order to differentiate them, we need labels, which is exactly what we did. We start by stacking and labeling the network. This is the first step and the most important step of the framework. In order to differentiate the layers, we need to label them to prevent that information loss we see earlier. And here's an example. If we're given 3 different social networks, we need to first turn them into a multi-layer network by defining the connections between the layers, like stacking them. So like this big matrix shown over here, the diagonal describes the connections within the layer. So for layer 1, its connection within will be this matrix over here. And the rest, the matrix that are not on the diagonal, describes the connection between the layers, which is just a vertical connection we saw earlier that represents their clones or the same individual. We then label them with the layer number and their ID. Now we're ready to feed the network into the model. So during the model initialization, the model are able to read the label and construct the agents accordingly. This enabled us to differentiate the layers during simulation. And now the model is ready, we can run and update our functions and synchronize the agents at the end of every time tick because they're the same individuals on different layers. Like shown here, we see the spreading process indicated by this color change. The vertical nodes light up together, which is our synchronization process at work. And this seems very straightforward, and it does work. However, it's very, very slow. As shown earlier, when stacking the networks, the memory allocation is O n squared, and synchronization also costs a lot of overhead. This makes the model impossible to scale. So we revised the framework and make some tweak to the framework. As you may recall, our goal is to differentiate the layers, and it turns out we don't need extra nodes to achieve that. Those nodes are redundant. Instead, we can merge the node across layers and represent them as single agent. The differentiation between the layers can be captured through the edges themselves. This gets rid of stacking and also synchronization, which saves us a lot of space and overhead runtime. So here's a more detailed look on how we achieve that, how we achieve layer differentiation by handling input. Instead of stacking networks, we use an edge collection approach. For each network file, we iterate through the data, and for every agent, we maintain a list of dictionaries representing its outgoing edges on different layers. If there are 3 network files as input, each agent will have a list containing 3 dictionaries, one for each layer. And each dictionary corresponds to the agent's outgoing edges within that specific layer. The structures allow us to differentiate layers at the agent level in a clean and organized way. And after collecting the edge list, we generate a single network file with each agent's edge list as compressed and stored as a JSON attribute. This approach reduces file size and allows us for efficient storage. The edge data is only decompressed when passed into the model, optimizing both memory usage and load time. Within the model, users can then activate specific layers by indexing into the corresponding dictionaries using the during the step function, enabling flexible layer-specific behaviors. So this is an updated graph. It is significantly simplified, with much of the underlying logic now handled by the framework, which allows users to focus solely on modeling the spreading process using their domain knowledge. And we ran a set of experiments to demonstrate the capabilities of our framework using a simple information propagation model. Each layer consists of 25 nodes generating using an Erdos rendering graph, and agents maintain a Boolean state to indicate whether they have received the information or not. And to reduce randomness, we seeded each node individually and ran the simulation 100 times per seed, resulting in 2,500 independent runs. The results are shown here. Traditionally, the node influence is measured using a degree centrality, which means typically it could be the number of outgoing edges within a single layer. However, our experiment shows that the node with the most dominant spread, which is the blue line curve over here, follows, it's not the one with the highest degree in either individual layer, but rather the one with the highest weighted sum of degrees across both layers. And this is captured by this equation over here, which defines that degree centrality equals the sum of the edges across layer weighted by the activation frequency of each layer. While this aligns with our intuition, our framework enables straightforward testing of such hypotheses through controlled simulations, demonstrating the utility of both the framework itself and the multi-layer network perspective. And to demonstrate the scalability of our framework, we later run a similar experiment with 50K nodes that ran on my computer, which is a consumer hardware with only 8 GB of RAM. And the runtime falls around 45 minutes to an hour, but with multiple core process, we could make this a lot faster. So for future improvements, we would like to enable dynamic edge to allow more simulation possibilities. Also, we would like to provide some standard benchmark to provide more statistic comparisons to custom approach. And that is my presentation. Thank you.
I think I need some more convincing that we cannot do this in the regular frameworks. For instance, NetLogo. From my experience, when you design the model, you already do a sort of dimensionality reduction that flattens these different networks or these different layers, and that's built into the constraint of what kind of model we're trying to make. So why would we need the multiple layers?
So you're saying with NetLogo, it flattens the network, and
or the person who builds the model.
Yeah, so flattening the network is actually what we want to avoid in the sense, like we want to label the layers so we can assign different frequencies. So for example, if I want to simulate how information shared across different social media platforms like Instagram or Facebook, the two platforms has different algorithms that spread the content, and it's also used at different frequencies. And in NetLogo, we are not able to assign different frequencies or update functions that in detail like we can do here with the custom model. Does that answer the question? So like with the agents, we can now separate them into different layers because they are distinct social networks with different attributes. And by separating them, we can assign different update functions or different frequencies with the framework and the platform.
Okay, I think I'm beginning to see, but I'd like to read the whole.
Yeah.
How about edge directionality? Could you have directional edges in one layer but not in another? I think, for example, a conference, if you go to a main session, most of the information flow is in one direction. If you're in a classroom, it's more bidirectional, or a workshop is more bidirectional.
So currently, it's only not direction, so it's like an edge exists.
Undirected.
Yeah, undirected. Yeah. So in the future, we could implement directional features to make it more custom to like different cases.
And that's consistent with the architecture. Since you attach a different frequency to each edge color, you could have a different directionality constraint to each edge color.
So the frequency kind of assigned to the set of the layer. So it's like so if this is a conference network, the frequencies is assigned to all the edge. So like when I activate this layer, it's the frequency of how much I activate the layer, not within the edge, not on the edge. But the edge can be adjusted like a normal simulation with floats to design the strength between the connections. But it would not be able to resolve the problem you stated, which I'm a presenter and I'm spreading information, and it's a one-way process instead of like a two-way thing.
So are you saying execution proceeds layer by layer? First, you do all the blue edges, and then you do all the red edges?
You can define the different time functions within the model, but yeah, it would be like one layer after another, even though they're on the same time step. Yeah. Yes.
I think this would be really useful. Like, I thought about how to do this with potential student simulations, and this could be a really good useful resource for my classroom. Are you planning to maintain this? I assume this is open source.
Yeah, it is open source.
Are you planning to like maintain it for a period of time of years?
So currently it's an individual project, so it might be a little hard. I do plan on like updating the framework to make it easier for unwrap and stuff like that. But maintaining would I have to like discuss with my PI to see if this could become a group work.
Yeah. Highly encouraged.
Thank you. Any other questions?
Okay, let's thank the speaker.
Thank you.
That brings us to the end of the program today. Thank you all very much for attending, for participating, presenting.
Thank you for sharing.